All right, so today we're doing the Ballistic Pendulum Lab. The idea is that we can determine the muzzle velocity, so the initial velocity of a projectile launched from a projectile launcher. Because if we know the mass of that projectile, and if we know the mass of the catch, then we can reason that all of the momentum from the projectile will be delivered into this system, and momentum is conserved. So we're sort of utilizing that conservation law to calculate our way back to how fast this was going. The data that we're going to collect is how much displacement there is in this pendulum. It's like how far back does it move. This apparatus is designed to sort of like measure it with this kind of a thing that probably needs to be fixed so it would work properly. All right. So this is the idea here. We'll start with the law of conservation of momentum. And again, the initial momentum comes from the dart itself. So momentum in general is mass times velocity. And so we're sort of applying this general definition to the sort of specific situation I'll have here, so the initial velocity of the dart. Once that momentum is delivered into the system, it's all going to be possessed in sort of like the dart pendulum system together there. So the mass of the dart plus the mass of the pendulum, one combined object. We need to have an inelastic collision. So if you looked at the slides and you went through them all, there are really two types of collisions, those that are sticky and those that are bouncy. Sticky collisions are inelastic, and this plus sign is the mathematical way to show that we have some new object now equal in mass to the sum of the masses. So we need to measure both the mass of the dart and the mass of the pendulum. And they will move together with some shared velocity that we usually call v prime. Okay? So here's the initial momentum from the dart. The final momentum will be the dart pendulum system, right? Some new object that's equal in mass to the sum of the masses, traveling at a shared velocity v prime. So it's unlike the example for the elastic collision where we still have two objects, that are separated, each have their own velocities, because it's a perfectly inelastic collision, which means, they stick together. So we just have one object, right? So mv, right? And the mass is just the sum of the masses. Ultimately, if you look at the data table that I think is already up on Instagram, there is not we're not going to actually vary, sort of one quantity against another. Back to my bartending days. You look at the data table here, I've sort of included the way to calculate each one of these other guys over here, all right? So X is really the thing we're going to measure. It's the easiest thing to measure for this lab. What we really want to know is like how high up the pendulum moves, okay? What we're actually interested in is the height that this thing is going to sort of raise. But you can see even like here, I'm comparing like this height to where it was down here. And so that's a hard sort of quantity to measure directly. It's such a tiny change in vertical displacement. It's easier to measure the horizontal displacement and do a bit of trigonometry and calculate what that angular displacement is. This one is actually designed to measure the angle directly. So this sort of thing stops at, and it gives you an angular displacement, 15 degrees, 20 degrees, and so on. With our apparatus, we could try to measure that directly too. We could set up a protractor and just try to get this measurement. We need some way to get ultimately to the height. Why do we want the height? Because we're going to use energy conservation. Potential energy due to gravity, right? It's based on the height that the thing increases in Earth's gravity field. So the data table here is really just going to be like every time we get a value for X, it's like one good data point, one horizontal displacement, and a good inelastic collision. Note the rough procedure over there. It says ensure an inelastic collision. If it's not inelastic, we need to do it over. So for every value of X that we get, we can calculate theta. We can calculate the height as L minus L cosine theta, where L is the length of the pendulum. And I'll kind of go through where all these equations come from on the whiteboard. All right, so we kind of know where that comes from. again, we're relying on the conservation of energy here, as well as the conservation of momentum, because it's oftentimes easier to measure the potential energy of something because we can measure its mass and we know we're in a certain gravity field G, and we can measure a height, something like stays at a given displacement, like a book, up on the television up there. It's harder to measure velocity, right? We've done it in the lab. We know we can measure velocity directly, or we can measure displacement in time and calculate velocity, but it's easier to just sort of rely on the conservation of energy here. Take a measurement of, X will ultimately lead us to H. Then we know the potential energy. That must have been equal to the kinetic energy just upon impact. Okay. And then we could solve for that value V prime, which would be unknown in this equation. If we knew V prime, we'd be done, because we can measure the mass of everything. So all of this is just to get how fast do they move together? What's that shared velocity V prime? And then once we know V prime, we can calculate our final claim, the initial velocity of our projectile. And again, this is up on Instagram, so take a look at that. Come back over here and see where some of those quick equations came from. That's our momentum conservation. And think about, as we're going through this, how you'll answer this essential question. How are these laws of conservation of momentum and energy utilized to determine this initial velocity of the projectile in our ballistic pendulum? So now we use energy conservation. We're going to say that upon impact, there's going to be some kinetic energy that the dart delivers into the dart pendulum system. Okay? It has momentum, and momentum is conserved. It has all the kinetic energy, but once it sort of crashes into the pendulum, now they're going to move together with some shared velocity. All right, and so that's sort of right at that moment, how much kinetic energy does it have? Right upon impact. And ultimately, all of that kinetic energy is going to be converted into potential because it's swinging on a pendulum. It's moving up in Earth's gravity field. So we're sort of relying on this equation that the kinetic energy of the pendulum dart system upon impact will all be converted into potential energy. Not really a valid assumption. We know there's going to be some other energy losses, but we're sort of assuming this. Okay? So the kinetic energy is 1/2. And at this time, we've ensured there's an inelastic collision. So it's the shared mass, right? The sum of the masses. So 1/2 m, and it's v, what we're calling v prime, and that quantity is squared. That's the kinetic energy. It's going to be equal to mgh, but remember m is still the combined masses, the mass of the dart plus the mass of the pendulum, 9.81 meters per second squared for g. And we'll talk about, what all these, inverse sine of x over L, L minus L cosine theta, that's the way we get h. But once we get h, we're relying on the law of conservation of energy to get us back to v prime. So if you just solve this for v prime, you get that. So the way that this is shown on the data table, we've already solved for the potential energy, right? We've already solved this. And so we just say, well, that's equal to this. And so we've kind of set all of this equal to, this over here, like we're calling this the kinetic energy equals this, right? And so we can solve for v prime as twice the kinetic energy divided by this sum of masses, and then the square root of that, right, to get rid of the square, all right? Let's just see that real quick. So this is the same thing as the kinetic energy, and the kinetic energy is equal to this. So we can kind of say the kinetic energy, which is the potential energy, is equal to 1/2 mass of the dart plus mass of the pendulum, v prime squared. And if you just multiply both sides by 2, divide both sides by this term, and then take the square root, you've isolated v prime. So that's sort of where that equation comes. Again, it's in the data table, but it's just using the law of conservation of energy. So it's the puzzle that we're sort of working backwards. We're saying we want to know this, and if we knew everything else, we'd be done because we know algebra, but we don't know v prime. So how can we get v prime? We're not going to use momentum conservation for that. We're going to rely on energy conservation because sort of velocity is what they have in common. They have mass in common to it. Right? And so let's remind ourselves how we're going to get H. Over here. So the students in class have to kind of dodge the laptop there. It'll all be up on YouTube later. You can watch it at your leisure. But now to the end of time, end of YouTube. We'll see what happens first. All right. How are we going to get H? So the dart crashes into the pendulum and it swings out some angular displacement. That angle we can call theta. And one thing that we'll have to know is the length of this pendulum string, L. Okay? Let me see if I've got a better marker. All right. So what we really want to know is this height, this increase in height that the pendulum undergoes here, like the vertical displacement. All right. It's actually moving this way, right? But all we care about is this. That's the work that's being done against gravity. Remember from last chapter, we said that work equals force times displacement. And the force to lift something is its weight, mg. And if the displacement is vertical, we can call it h for height. And so it really just comes from the definition of work. The work that we do lifting something in a gravity field is equal to the potential energy it possesses at that height. So we want to know this height. We know the length. When the pendulum swings out some angular displacement here, it is still L long, right? It didn't change its length, right? It's still going to be that length. In other words, as this thing hangs here, it's a certain length, and when it swings out, it still is that long, all right? But we can kind of think about, it's made this triangle here, where however far it goes back this way, it's easy to lay a ruler down underneath it and see how far horizontally it's moved. It's the easiest thing to measure. It's easier than, like, we could lay a ruler vertically behind it and try to, like, directly measure the height. We could put a protractor up here by the hinge point, try to measure this angle directly. That would be, helpful. But in my opinion, the easiest thing to measure is this horizontal displacement that I'm calling x. Okay? By just laying a ruler down, sort of underneath the apparatus, and just measuring from the pendulum started here, and it swung back here, and you're just sort of eyeballing. Or you can use other, like a slow motion camera, put it up here and actually see, pause the video and get a really good reading of that. Now we can see that this component, like from here to here, is L cosine theta. We took the cosine of this angle. The cosine of theta equals adjacent. So now I'm talking about this triangle right here. Okay? Because that's where the pendulum sort of goes. So I know the hypotenuse L, and this is what I can measure. So the cosine of theta is adjacent. Okay, so it's like this little bit from here to here. Right? Not the whole length, but just like this much of it. Okay? Adjacent over hypotenuse. Let's just call this like lowercase a really quickly for adjacent. All right? So the cosine of this angle is the adjacent over the hypotenuse. Right? And if we really want to know what a is, we multiply both sides by L, and we have L cosine theta. So remember, I just sort of temporarily called this called this A, this piece of it. But what it's really equal to in terms of theta is L cosine theta. It's the component of L, that's sort of like this much of it, right? The component of this triangle. So from here to here, we've got L cosine theta. If this whole length is L, and this much of it is L cosine theta, and we're interested in this difference, H, that's why H is L minus L cosine theta, okay? That's kind of confusing at first. It kind of still is for me, okay? But if you work with that for a moment or two, and just kind of work with this triangle, you'll hopefully prove to yourself that H is indeed equal to the whole length L minus this much of it, L cosine theta, okay? So L minus L cosine theta. How can we get theta, though? In other words, we need to know what the angle theta is to get H. How are we getting that? Okay, well, if we measure X and we know L, what we really need to do is relate the opposite to the hypotenuse, and that's the sine function, right? So we can actually get the angle theta by saying the sine of theta would be X over L, okay? The sine of theta would be X over L, so theta is the inverse sine of X over L. And again, I'll put a link to the video where I sort of explain the lab, and I kind of go through this and these explanations there. But it is helpful to draw this figure for yourself and kind of think about where these numbers come from. The rest of the lab, once we sort of get to the fun part, which hopefully is today, sorry for that. 901. It's a lot of calculations. There's a lot of calculations. So that's what I mean by get to the fun part. Get to do the calculations. But first, what should we do? What's the first thing we should do, class? Oh, because that's what's that. That's true. That's really like the procedure. But if we did this and then we measured X, then we have to, when we did our analysis, be like, oh, you got to measure and record. So this is our time to break open some fresh chalk here, so we won't make a mistake. And in the spirit of tomorrow being October 1st, we'll use this. You can see the orange chalk here. And we'll call this the 0th step. Oh, that's not quite the orange I wanted. Come on this way, class. Okay. The 0th step of the lab I don't know if I like all this. So like coloring it because it's orange and then black behind it. I have to do better. All right, in my opinion, a jack-o'-lantern should be kind of scary looking. If you like a this kind of that almost looks creepier actually. You get the idea, okay? A scary looking jack-o'-lantern rather than the guy over here. That's the 0th step, the pumpkin step, okay? So let's measure and record the mass of our projectile, and it's a dart, so the mass of the dart, mass of the pendulum, m sub p, and the length of the pendulum, and we need to set up some apparatus and take some measurements here. So the dart does have Velcro on it, and the pendulum target also has Velcro. All right, so that will ensure, hopefully, our inelastic collision. For the mass of the dart, we have 1.5 grams, which is what? .5 grams is 0.0015 kilograms, right? Yep. So the mass of the dart is 0.0015 kilograms. The mass of our pendulum .45 45.7 grams is 0. What did I say? 45.7? 457. 0.0457. Note how the pendulum is like an order of magnitude more massive in an odd factor output. The length of the pendulum, we'll need to set up our apparatus now. And set up here on this side. I think we'll just keep with that. Let's see here. I like this particular lab bench for this experiment because walking by, what's going on in there? We'll find the cool lab away. As a safety precaution, I'm wearing my closed-toed shoes and a face shield, too. Notice that. But in all seriousness, as a safety precaution here, we always set up the ballistic pendulum so that we're never firing across students or any human. So into the wall. Okay. Now the way it is now, like this side of it, a little lopsided, so if we hit it, it's going to tend to spin like that. Spinning costs energy, right? We're sort of relying on the fact that when this dart impacts the pendulum, we want as much of that energy to be transferred, you know, this way, right? So it elevates. So we don't want to hit it like off center and it starts spinning or anything like that. So you might need a quick adjustment over here. And this is the stuff like when you do lab work, which kind of like in this year, you know, have to do as much hands-on stuff. But it's the only way that you can learn is by doing. And it's kind of like, what do I do with this? Like troubleshooting, you know? Like, what would you do to solve that? Maybe make this one a bit shorter, tie it up here. Maybe like, if you really cared about your you know, lab work and accurate conclusions, maybe you'd like replace these strings with something else. I just saw RTC march by, and I feel like that's because class is about to end. Precariously situated there. That made it worse, not better. All right. Of the pendulum string. And so we're going to, even though there's two strings here, we care sort of about this vertical distance. And I'm getting 60.8 centimeters. So 0.608 meters. So everybody following along at home? We've got the mass of our projectile, 0.0015 kilograms, the mass of the pendulum, 0.045 kilograms, and the length of our pendulum at 0.608 meters. Now, get a really cool perspective. Stand by. All right, so how would you like to launch our projectile into it? Who's got a good throwing arm? Anybody play darts? You got a better one? All right, we've stored some energy in a projectile launcher. We've stored some energy in the projectile launcher here, right? By pulling this back, so there's a spring mechanism in here. We'll convert some of that. Anybody remember? Elastic potential energy, good. Into kinetic energy of motion. This has mass, it will have velocity and therefore momentum, and we'll deliver all that momentum into this system. Oh, I suppose we need to like do some science too, right? Lay the ruler down. And I have a true mark at 20. All right, and so really what I've had students do in the past is put like a slow motion camera from this perspective and then do the lab and then play it back, and you get a really good accurate reading of how far back, you know, the pendulum sort of swings that way. So that's kind of what we're trying to eyeball here in the lab, get a measurement of X. So I think this is also for anybody watching on YouTube later. I'm recording this. All right, point blank range is what I suggest to students as they're just collecting the data. And then you can have fun, like, you know, take 10 paces back and launch and get, you know, from the crosser and that sort of thing here. All right. Are we recording? Yeah. Good. And so that went as far back as 26 centimeters, okay? But it's starting at 19. Starting at 20. So it was displaced about 6 centimeters. Let's check it again. Are you rolling? Lab partner. Right. Come on over here. So you just put some eyeballs on and use your judgment to tell me how far back. So it's like I'm calling 0 to 20. So you just kind of just find how far back. What would you say?
Like
27,
28.
28? Yeah. So I thought 6 first. One of the lab partner to sort of corroborate my claim here. One more. And obviously some uncertainty in the apparatus itself. Probably not every trial is going to be exactly the same. So we get one more data point. That's a do-over. Same thing like 28, I think.
Yeah.
You can kind of see like, it does lose energy, obviously. Like now it's oscillating like our pendulum before. It's losing energy as it's crashing into air. But like the first oscillation or two basically has as much energy, so it's going to kind of go back almost as far. Thanks, Brad. I appreciate that. So we'll say 8 centimeters then of displacement. Now for the fun part. The calculations. All right. We got a displacement of 0.08 meters. The initial length of the pendulum string was 60.8 meters. So we're taking 0.08 over 0.608. That ratio, the inverse sine of it, gives what? Once you took the sine, okay, so the ratio is 0.1315, and then you took the inverse sine and you got 7.6 degrees. So we get theta, 7.6 degrees. Why do we want theta? So we can get L cosine theta and take that away from L. In other words, the actual increase in height was that full length L, 0.608 meters, minus this little bit of it, L cosine theta. Note how small of an angle theta is, which is why it's hard to measure that directly. And wait till we see what the height value is. So I got my 7.56 value in my calculator, and I'm going to take the cosine of it. And it's almost 1, right? 0.9913. So a number that's almost 1 times the length times 0.608 gives me a number that's almost 0.608. It's 0.602. Okay? So this is like 0.6027, and I want to take it away from the 0.608. So my calculator is going to make this negative. Okay? And I'll add it to. In other words, if I can just keep everything in my calculator, I'd rather do that. I'll like write something down, it takes like a half a second to do that. So I'm going to make this negative, and now I'm going to add the 0.608 original length to get an h of 0.0052, and I am in meters because I converted all these to meters. Okay, so I don't have to duplicate that here. So it's what, half a centimeter. Okay, 5 millimeters was the actual increase in Earth's gravity field. Not a lot of energy then, not a lot of potential energy, right? We barely increased its height, but it's, you know, calculable, maybe not measurable. It'd be hard to lay a ruler vertically and go, oh yeah, 5 millimeters. See what I mean? So it's like, yeah, more math, but that better, you know, result. Now we've got h times 9.81 times open parentheses. I'm going to sum these masses here. So we had 0.0015 plus 0.045, close parentheses. So 0.0465. I'm going to hit equals. It's multiplied all those, and I'm getting, check me in your own calculator class, 0.00024 joules of potential energy. Really 0.0024 joules of kinetic energy, right, that it had upon impact. That was the kinetic energy we're assuming was all converted to potential energy as that system of masses swept up to that height, right? Swept out this angular displacement, 7.6 degrees, therefore a height of this, therefore an energy of this. We set that equal to kinetic energy. Like the kinetic energy is this, same as potential. So now we take twice that. So I got this in my calculator, times 2. Okay, now I want to divide it by, again, open parentheses, the sum of masses, 0.0015 plus 0.045, close parentheses. Maybe it's helpful to like mp plus mp equals 0.0465 kilograms. Keep that off to the side. So then I kept that in parentheses. So when I close parentheses, or when I hit equals, now I've evaluated everything under the radical. How do you take the square root of something in your calculator? Some calculators, you just hit the square root function, and it will evaluate whatever's in the display. Other calculators, once you hit square root, it opens up parentheses. You got to retype that in. So if you already have a value in your calculator, if you have one of those calculators that requires you to like put back in the value when you hit square root, just raise whatever's in your calculator to the 1/2 power. That's sometimes easier to just calculate. It's like caret, right? Raise to the 0.5. Raising something to the 1/2 power, same thing as taking a square root. So my calculator, I can actually just take the square root. If I wanted to, I could hit y to the x, so raise to the 0.5, same thing as taking the square root. Sometimes it's easier to compute it that way. So now I'm getting a velocity, right? V prime, the shared velocity of the system upon impact, 0.322 meters per second. Yes.
For height, I keep getting something different when I calculate it.
Is it kind of close though?
It's 0.054, so like I'm missing a whole like 0.
0.054. So just check like the place value. Like this cosine something is almost 1. So when you multiply it by 0.608, you get a number that's really close to 0.608. Like just check it again. Is anybody else having a discrepancy here? It's very possible I made a mistake. Like when I see like 6 students in class go, that's you know, then it's like, okay, I made a mistake. But if everybody's like, no, I got that, then it might be that you made a mistake. And it's okay to make a mistake, like we just need to figure it out amongst ourselves here. Okay. So check your calculation, and if you're still getting that, like we'll figure it out together. It's like I'm still getting this. So,
Yeah, I still am.
all right, sometimes it's worthwhile to actually see. Okay, so tell me what you're typing. So go.
6.08 minus 6.
It's not 6.0. It's 0.608. Okay, so sometimes when you're off by like a whole order, it's just like a decimal's wrong somewhere. A conversion is wrong sometimes. It's like, oh, I didn't go from centimeters to meters or something like that. So remember, the length is 6d centimeters, so it's 0.6 meters. 0.608 is what L is. All right, so now we've got our V prime. We need to multiply it by this term here, which is the sum of the masses divided by the mass of the dart. Remember where this comes from are momentum conservation, right? So this is using momentum conservation now, or I use energy conservation to get V prime. Now we know V prime, I'm going to multiply it by, so times, open parentheses, I already know the numerator, 0.0465 divided by the masses are 0.0015, close parentheses. So like, what's this? This is 31, even. Let me get this up. So this term right here is 31 times 0.322 equals 9.9810. 10 meters per second. Time to spare. I was getting kind of nervous as I began these calculations that we would run out of time before I got to the end, but then I felt like, you know, if we just kind of go through, we should be able to get it done okay, and we did. Well done, class. Because I always, you know, I say like, you know, we're doing all this testing, and it's like, when are we really going to be in a time crunch to like do our physics calculations? You know, like a meteor's coming for Earth, you know, and like need the physicists to calculate how we'll launch this, you know, rocket. It's like, well, we're doomed, you know. It's like now it's a time crunch. It's like, oh, good thing I took all these high stakes time tests in my physics classes, right? Now I can, you know, work under a time crunch, and I had that feeling just a moment ago where it's like, oh no, the bell's going to ring. Now's the time to shine. Okay, now since all this testing is going to pay off, we're going to rush through. But do we make a mistake? I don't know. I mean, we can also make mistakes too. So it's like, oh, it's better take the time. I don't know. But anyway, we got a conclusion. Any questions about that? Till next time.